Hello, welcome to this next video in the Rocket series. So as promised, we're going to have a little blast through this wonderful bit of software that allows us to design and simulate model rockets, high power rockets, mid power stuff. It's really versatile. So the first thing you need to do is download OpenRocket. If you Google OpenRocket, you'll find a link to download it. It's a Java application, so you need to have a Java runtime installed. If you don't know what that is, I suggest you just download it and click to open it and see if it works, because you might have a Java runtime installed. If you haven't, Google again installing a Java runtime, and I'm sure you can get yourself sorted. So when you open OpenRocket, you get this kind of work area. Your rocket's going to appear down here. There's some info, there's some tabs up at the top. If we go to File and just click Open Example, let's click a simple model rocket example. It opens up and you get this rocket configuration dialog box, which is basically just a place where you can put your name, the designer, and some comments. I quite often use that for making little notes about the rocket, particularly if it's something that I'm going to design over a longer period of time. You can get back to there by clicking this, double clicking that bit there, and you get that kind of note section back. You can see here we've got this kind of file tree system, and if you click on each of these, it selects the corresponding part in the view down here. Don't worry if you don't know what all these parts are. Yeah, I think that'll do for now. So let's just click File and New, and let's very quickly design a rocket. So when we're starting a new rocket, it always either starts with a Nosecone, a body tube, or a transition, and indeed it always adds things. If I click on Nosecone now, oh, I've added two there, so that's not a very good start, is it? Close. Well, it shows us, it gives us we can, if we select things up here and simply press delete, it shows us how we can get rid of things. So in fact, let's delete that one, and so if we click this once, what we get is the Nosecone appears and you get a dialog box into which you can put all the details and parameters for this Nosecone. So we've got some shapes of Nosecones. We've got conical ones, we've got ogive, I never quite know how to say that, ellipsoid, and then there's things like the power series, parabolic series, and Hark series. They're types of Nosecones that have been developed in the Rocketry community, and they're included here. Interestingly, you can find 3D models of all these Nosecones, so they're all kind of makeable. We're not going to go in depth about all the kind of things, but we'll change we'll leave the length as it is, but we'll change the diameter down a little bit so that it's a 3 centimeter build. Leave this automatic thing ticked here, and the wall thickness is basically how thick the material is. So that's 0.2, that's 2 millimeters. Incidentally, you can change all of these, and you can change them in preferences if you prefer to work in millimeters. For every component that you add to a rocket, you'll get a component material drop down. So it's got, you know, metals, woods, all kind of common materials that we build stuff out of. So a common material for a Nosecone might be balsa, but increasingly we might print them out of plastic, or we might buy them in a plastic. So I'm going to put them in PVC, which is sort of heavier, but it's more likely, so I might not actually make this out of PVC, but I might 3D print it and it might come out in a similar way. Interestingly, what I do to dial in my sort of simulations and my designs is, after I've created a component, I'll come back to my design in here, because every component has an override tab. And particularly, you can click this button and override the mass. So instead of it being whatever it calculates for the size of the component and the material you've selected, you can actually come back and override it here. And after you've weighed it, so print it or carve it or whatever you're doing from balsa wood, and then weigh it on some scales and come back and put the actual weight in. But for now, we'll just leave it as it is. You've also got a component finish, which is whether it's rough, unfinished, regular paint, smooth paint, or stuff. I tend to leave stuff at regular paint. I imagine my finishing skills actually make it slightly rougher than that, but there we go. So we'll oh, actually, before we go, most nose cones will have a shoulder. So for this shoulder, let's set the shoulder diameter to 2.6 centimeters. And let's put the length of it to 2 centimeters, say. And there we go. That would be the bit that would slot into our body tube. Now, interestingly, we've set this internal, outside diameter of the internal shoulder to 2.6 centimeters. And what we're going to do now is come out of there, select the nose cone, and we're going to add a body tube. Now, because we've got this automatic thing clicked, it's picked up that we want the internal diameter of the body tube to match the outside diameter of the shoulder of the nose cone. So it's set it to 2.6 and put the wall thickness at the same. So all these kind of match. It leaves a gap so that we can see the separate components, but it's actually considering that those now fit pretty snugly, like a sliding fit inside each other. So for this body tube, we're going to increase the length. I don't want a 20 centimeter rocket. I want let's go up to 40 centimeters. Yeah, I think that will do us. Material, yeah, we'll have it as a cardboard tube, and again we'll leave it as regular finish, so close that one. Now, you might notice that there's lots of other things that aren't sort of selectable, and so it's because we need to have something selected for it to allow us to kind of add things to it. And sometimes what you've got selected dictates what you're allowed to add to it. So like, for example, if I select the nose cone, it's unlikely that you'd want to put fins on a nose cone, so it doesn't let you put fins on a nose cone. So if we select the body tube again over here, just by clicking on the icon, let's add some fins next. So we've got different types of fins. We've got freeform ones, which you can draw in, rounded ones, or trapezoidal ones. Let's stick some trapezoidal ones on. So again, they appear down here, and we get this kind of dialog box. So obviously we can increase or decrease the number of fins. 8 fins, that would be a lot of work and a lot of drag. Let's go. 1 fin would maybe not work so well. Oh, well, you know, maybe Elon Musk might disagree. 3 fins. Let's go for 3 fins. Let's ignore the rotation. Let's make them a little bit smaller than this. So the root chord is this length here. The root chord is the length across the bottom of the fin where it joins the body. So let's take that down to say 4. Now that's an odd shape. We want the tip chord, which is obviously the length of the top of the fin. Let's turn that down to say 2. Oh, I don't like that. Let's make that 4 and 3. The height is probably a bit high. Let's go for 2.5. There we go. Let's leave that now. Apart from, we don't want our fins to be made out of cardboard. So common for this sort of size rocket, maybe balsa wood would be a good one. Interestingly, you have this other thing called root fillets, which is where when you glue fins onto a rocket, you might often put like a kind of fillet of glue down here to reinforce them. We're going to leave those for now, but it's worth knowing that you can add like a kind of, like if you're using a fiberglass or epoxy to attach your fins, you could add that there, and then of course it would be included in the simulation. Oh, the other thing that's interesting about fins, fin cross section, it gives you and the thickness. So this is made out of 3mm wide balsa wood. Let's change that to 2mm perhaps on this size rocket, maybe, I don't know. And the fin cross section is like the leading edge of the fin. Do we want it square? Do we want it rounded or airfoil? Now rounded is quite easy to do. We can sand them into a round shape. Airfoil is like that kind of long teardrop shape, like the shape of sort of you know, some airplane wings and things, which is harder to kind of do, particularly at this scale. People do it, don't let me put you off, but that airfoil is like the least kind of drag inducing, so it really slips through the atmosphere well. But square is the least because you've got a square edge kind of hitting the atmosphere, but rounded is probably quite achievable, so let's change it to rounded. Okay, I think that'll do us in there for now. Let's close that. So we've kind of got a basic shape of a motor, of a rocket rather. Interestingly, we can change different views here. We can look at a sort of 3D figure where it's undone, and we can spin the rocket round. We can look at a 3D finished, and we can change the colours and the components, and we can paint it and do all kinds of things like that. For now, let's go back to the side view. So there's a couple of things that mean this rocket wouldn't fly. One is it hasn't got a motor, and it hasn't got anywhere to put the motor. So the next thing we're going to do is select the body tube again, because we want an inner tube to go inside the body tube. So let's click the inner tube. Okay, so it's actually added a pretty decent inner tube that we might use as a motor mount, and it's in the right position. That's probably because it's kind of used to the choices I've made before when I've been making other rockets. So let's just have a look at this. So it's put in, let's make it a bit longer, maybe make it 10 centimeters. The outer diameter is 1.9 centimeters and the inner diameter is 1.8 centimeters. Okay, we're going to leave that at that because 18 millimeters as an inner diameter is perfect for a really common size of motor. So there are quite common diameters of motors out there: 13 millimeter, 18 millimeter, 24 millimeter, 29 millimeter, 38 millimeter, etc., etc. You get quite used to kind of thinking in terms of motor size. So this motor tube is looking okay. Sorry, this inner tube is looking okay. And the component material, cardboard, that's fine. At the moment though, the program OpenRocket just thinks of this as a random tube. So what we've got to do is we click this motor tab here, and we're going to check this box. This component is a motor mount. There's some other things here, but we're going to leave these for now. So we're going to leave this ignition, and we're going to leave the motor overhang. Basically, is if the tube was shorter than the motor, how far would the motor hang out of the back of this end of the motor tube? Okay, let's close that for now. Obviously, in real life, this motor mount wouldn't really exist. It wouldn't just hang in the middle of space in that tube. It would have to have some centering rings. Now, I'm going to show you this mainly because it shows a common mistake. Sometimes you need to have the parent kind of object that you want the centering ring to go into selected, rather than the object you want to surround. So if I have the inner tube selected and I click centering ring, it actually puts a centering ring inside the motor mount tube, which we don't want. We want it to be on the outside. So if we close that and just select this and tap the delete key, it will get rid of it. If we click the body tube again and add a centering ring, you can see now it's added a centering ring that's around the motor mount tube and inside the body tube. It's automatically made it reasonably the right size. You might want to make it thicker, 2 millimeters. You might want to make it 3 millimeters. Might not want to make it out of cardboard, although some are. Again, balsa might be a good one, or plywood is in here. So let's make it out of balsa. Let's leave it there. That one's in the right position. Now what we can do, instead of going through all that again, to add another one, because normally you'd use 2 or maybe even 3 centering rings on a motor mount tube, let's do if we hover over this and hit Control C and then hit Control V, it adds another centering ring. If we select that second centering ring, we'll notice that it's exactly the same, which we want, but we're going to move it. So most components we can move, and we move the position relative to different aspects of the parent component. So we could say relative to the top of the parent component, so that would be this end of the body tube, the middle of the parent component, or tip of the nose cone. Let's leave it at the bottom, and then if we reduce this, we can see over here, we can see that this centering ring is moving up. So let's move it up to the top of the tube and leave that there. Okay, we've got a motor mount tube. The other thing this rocket needs is it needs some way of recovering. Remember in the first video we talked about the push out parachutes on the motor ejection. So let's again select the body tube, because that parachute would go in the body tube. Click the parachute button, and it makes a parachute. You can see it here, it's all kind of packed up. It's 30 centimeters diameter. Let's leave that for now. It's made out of nylon. We can change the position, so maybe let's move it down a little bit into the body tube, and we can change the pack size of it. So it's unlikely that you would fold that up into a 2.5 centimeter cube, so let's make it a little bit longer. The number of lines you can change, we can change the line length. Let's not worry about those for now, so let's close that. So now we have a parachute. Okay, so I just want to mention these numbers over here and these two icons. So we talked a little bit in the first video about the stability of rockets, and that this point the center of pressure needs to be behind the center of gravity. So the center of pressure is behind the center of gravity here, but it's quite a long way away, so it's overstable. We ideally want the stability number to be between 1 and 2. Opinions differ on that, so do read around and read up on stability, but I've always aimed for between 1 and 2. So interestingly though, when we add a motor into the motor mount, that's going to add weight to the back of the rocket, so I'm pretty sure that this centre of gravity is going to move backwards. So let's do that. So if we select the inner tube, that's a motor mount, because remember we ticked that box. We then go to, actually we didn't need to select that, you can select anything here. What we need to do is select the motors and configuration tab. There's no motors or no motor configurations added, so we're going to click new configuration, and then down here we'll click select motor. Now the motors quite often, so over here we've got the manufacturers, and these are all the different manufacturers that exist in the world who make kind of make model through to high power motors, and here we've got all the motors kind of that they create. Oh, let me just change that. Oh no, hang on, I've done something wrong there. There we go. So that's basically, you know, all hundreds of motors that are available. Now, of course, trawling through this is a bit of a pain. So there are numerous ways that you can constrain this list to get to the type of motors you want. So remember, our motor mount tube is for 18mm motors. So what we could do is limit the motor, is click this button, which was already clicked actually, sorry. If we click that, it would limit the motors that we can select to between 0 and 18mm. If we bring this up, it will limit them to between 13 and 18mm, and if we put it on there, it just gives us all the 18mm motors. I know that in the UK a lot of these companies' motors are quite tricky to get though, so what I'm also going to do is clear all of these and then just click Estes, because most of those are kind of available. Okay, so I know that I've got some Estes B64 motors. Again, we'll do another video where we'll talk about the kind of numbers and the power and the stuff to do with motors. But for now, I know that I'm gonna select one of these B64 motors. So we select the motor here, but before we click OK, we need to set the ejection delay charge. Now I know that on these motors are available with a 2-second delay, a 4-second delay, or a 6-second delay, and that delay, if you remember from the first video in the series, is the delay from after the motor burns out, the rocket carries on coasting up, and the delay is burning inside before it kind of blows the deployment charge. So I reckon I've got in my box some B64s, so that will give it 4 seconds of delay. We're going to OK that, and you can see it's chucked a motor in there. Okay, so this rocket is kind of getting there now, and we've got enough information in this design to run a simulation to see how well this rocket flies. We are a little bit overstable, so we're at 2.68 here. So what I might just do is I might go back to the rocket design, and I might just decrease the size of those fins a little. So let's turn that height down to 5 and see to 2, sorry, by 5mm, and see what that does. That's brought it down lovely there. So we're at 1.4 calibers of stability. Caliber means the diameter of the main section of the rocket. So actually this distance here is 1.4 times the diameter of this rocket. Okay. There's loads of things in real life that would mean this rocket wouldn't actually work. For example, we haven't actually put any shock cord to attach the parachute to this. to the airframe. We haven't added any motor mount sort of blocking disc that would stop the motor from coming this way, or any way of retaining it. We haven't even got a launch lug, which we could actually, let's just add a launch lug. A 1 centimeter launch lug would be quite wide. So the launch lug, if you remember, is the small tube that attaches the rocket to the launch rail. We can add this if we like. So we'll put the outer diameter at 6 millimeters. There we go. Change the inner diameter to 0.4. That will kind of do for now, but it wouldn't need these components. It doesn't need these things to be a complete rocket in the design to simulate them. So this would give us a rough, there's enough information here to give us a rough simulation. So if we click flight simulations now, and we select, this is an unrun simulation, there's no data in these columns here, but we can see it's for this motor. So if we click run simulation, it runs the simulation. We get some data, so we can expand these columns out and look at them. So this, for example, is the velocity off the rod, so the speed at which, the velocity at which the rocket leaves the end of the launch rail is 13.5 meters per second. We've got the apogee, it goes up to 70.2 meters, not the most optimizing rocket. Optimum delay time, blah blah blah, other stuff that we've got. Time up to apogee 4.09 seconds. What's important to notice is we've got a green tick here. If something in the simulation isn't correct, or if there's something that OpenRocket is concerned about, so say for example we deploy the parachute on the way up because we've set the delay wrong and the rocket's going far too fast and it would rip itself to pieces, this will come up with won't come up with a green tick, and when you hover over it, it will tell you what it's warning you about. Okay, so that's the simulation, but let's now click the plot export button. Let's ignore this bit and just click plot at the bottom, and what it does, it gives us a nice graph of our flight. So the red line is the altitude, so we can see here the rocket goes up, it hits the top, it's marked apogee, and it starts to come down, and we can see not far after apogee we deploy the recovery device, so the parachute comes out. We could actually see, if we'd left that a little bit longer, that it would start to fall quicker and then it would level out a little bit as the parachute slowed it down. We've got some other information. We've got vertical acceleration, so on the green line, so we can see actually here as the parachute comes out, it increases the vertical acceleration as the drag of the parachute comes into effect, and we've got the point at which the motor burns out. So there we go. That's a pretty simple rocket that we've designed. Goes up to 70 meters. It's probably not the most efficient rocket. I'm sure on a B64 motor you could build something that goes much higher. So there's a little challenge for you. I hope this has been useful, and I hope that it gets you started having a play with OpenRocket. Okay, ta-ta for now.